Hello. So we continue our topic on tangent plane and normal line to a surface, right? Yesterday we solved several problems on tangent planes and normal lines. And the main idea is the following. Let me remind you a little bit from yesterday's lecture, and then we will finish this section, right? So the idea is if you have function z equal to f of x and y, you write this function as, I will put f capital X, Y, and Z, and this is equal to Z minus f of X and Y. And since Z equal to f of X and Y, this function is identically equal to 0. So our surface Z equal to f of X and Y is just a very special case of the level surface of this, okay, of the level surface. So, and we know from the very first chapter, not from the very first chapter, but from previous sections that, gradient of the function f capital is perpendicular to the level surface, to level surface at each point. So that's why, in order to find the tangent plane to the surface z equal to f of x, we just need to find a normal vector, right? We need a normal vector. And this is normal vector, nothing but, it's just gradient of f. And if they give you one point P, like x0, y0, and z0, so you can write the equation of the tangent plane. So we can write a tangent plane. And the equation looks like gradient f dot product with px, okay, dot product with px. So this is equal to 0 because px is perpendicular to delta x, to delta f. That is about, the tangent plane, okay, about a tangent plane. About normal line, actually the normal line is right here, right? In the same situation, the normal line will have direction vector gradient of f. So if they ask you to find normal line to a surface as a given point, so you already have gradient of f, and then you use canonical form, or you can use parameterized form, okay, to write the equation of that normal line. So let me remind you about this, right? Canonical form. So you would have the following form: x minus x0 over. I would write in here. Let's say f partial derivative, okay, with respect to the x, and then y minus y0 over f partial derivative with respect to the y, and z minus z0 over f partial derivative with respect to the z. Because component of gradient of f capital is just fx, fy, and then fz. So we can write in that form, or you can write in the parameterized form like x, y, and z. And here you have x0, y0, z0, plus I write fxt plus fyt plus fzt. That's it. So that's what we did yesterday, okay? Well, we did yesterday with just one surface. And now, let's consider the following problem. Let me show you the picture, okay? And then I will explain you how to do that. So the picture look like this. Example 5 in the textbook, find the equation of a tangent line to a curve, okay? So in this situation, you see, they give us two surfaces, and two surfaces will intersect by a curve, right? You can see from here, by some curve in here, and they ask us to find the tangent line to this curve at a given point. I remind you about a problem we did when we study vector functions. So when we study vector functions, we know that vector functions are very good to describe curves, right? And we know how to find tangent line to a curve, to a straight curve with the vector functions. And now they don't give that. They don't give us vector functions, right? They give us two surfaces. But you know, you can find the intersection of these two surfaces. Make sense? And then you can use like you can write, you know, the intersection as a vector function. It's very easy. Let me show you that, and then we will explain the idea they use in this situation. Okay, so if you have one function, one surface x squared, okay, plus 2y squared plus 2z squared equal to 20, and another surface is x squared plus y squared plus z equal to 4. So basically you have, in order to find the intersection of these two surfaces, you need to solve this system. And the system has only two equations at the same time, but you have three variables. So that means one variable should be parameter, right? One variable will play the role as parameter. So that means you can describe, like you can put z equal to t, x equal to t, or whatever you want, right? And then you solve for the rest of variables. So you will have, you know, a vector functions. Make sense? Like, for example, you can put, let me see, we can put z, or you can put x equal to t, right? For example, you put x equal to t, and then you can write your equations, your systems will become like 2y squared plus 2z squared equal to 20 minus t squared. Another one is y squared plus z equal to 4 minus t squared. And from here, if you can solve for y and z. So you will have two functions, yt and zt. Makes sense? And then, you know, you can express your intersection as t. So I can write here intersection means the curve. Intersection is t, yt, and then zt. And of course, that is your rt. And we just come back to the situation of vector functions. And you know how to find, you know, tangent plane, right? A tangent line at a given point. So you can go back to the very first chapter in our course, and you take the derivative of rt, and then, you know, so on. rt, and then I think I remember that you can find tt, that's it, r prime t over rt, right? Norm. So you have to go a very long way, right? And if they give you a point, like they give you a point, for example, when x equal to 0, y equal to 1, and z equal to 3. If they give you this point, that means t is equal to 0. So that means t equal to 0. T is equal to 0. So you plug t equal to 0 into tt to find the direction vector, and so on. You can find the equation of tangent line to this curve. You know, this is a very long way, right? So now we already know how to find normal line to a surface as a given point. So now we have two surfaces. We will use that technique, you know, to solve this problem. Okay. So let me remind you, right? Let's repeat again. They give us two surfaces, this one and this one, and they give us one point in here. They ask us to find the tangent line to the curve. Okay, let's find the tangent line to the curve. All right, here is the idea. Let me show you again the picture. Okay, so here's the idea. So they ask us to find a tangent line. Right here we have intersection. So in order to find a tangent line, we know that tangent line is perpendicular to the normal line of each surface at that given point. Right? You can see right here, you know, this is the point 0 and 1, 3, right? You have tangent line. And the tangent line is perpendicular to each normal line of each surface at this point. So I have the following one. Let's write it down, right? The tangent line is perpendicular to normal lines. Normal lines. Okay, I write S in here of the surface. Surfaces. So what is that? If the tangent line is perpendicular to two normal lines, so that means the tangent line is just, you know, a scalar multiple of the cross product. So you might think about cross product. Is it correct? So if you have two normal lines and you take the cross product of these two normal lines, you get the direction of the tangent line. You are good. Make sense? So that is the main idea. You need to find cross product of two normal lines to the surfaces. And we know that what is the normal lines? You know, that is just right here. If you have function z, you can find f capital equal to z minus f x and y, and the normal line is just gradient of f capital. Okay, all right. Now I think we already have all tools, all ideas, right? Let me put out these two equations and then write two f capitals, right? All right, let's solve this problem. Now here's the solution. The first one, I write f1 x squared, I'm sorry, it's just not x squared, it's just x, y, and z equal to x squared plus 2y squared plus 2z squared minus 20. That is f1. I have f2, x, y, and z equal to x squared plus y squared plus z minus 4. And then in order to find normalize of these two functions, I just need to find gradient of f1 and gradient of f2. Okay, this is two normalized. So I will differentiate partially with respect to the x, y, and z. I have 2x in here, I have 4y in here, and then I have 4z in here. Or I can write in short just 2 times x, 2y, and then 2z. Okay, gradient of f2 is 2x, 2y, and 1. All right, so we already have gradients of these two functions, and now we just plug x and y and z into these two gradients to find vectors. So I have delta f1 at 0, 1, and 3 is just equal to let's say I can write in here 0, 2 times 0, and then 2, and then 6, or that is just, you know, 0, 4, and then 12, right? Another one is delta f2 at 0, 1, and 3. Gradient of this f2 is equal to 0. 2 times 1 is 2, 1 is just 1. So, and then after this we need to find cross product. We need to find cross product of gradient of f1 and gradient of f2. So I have cross product of these two gradient is equal to I, j, k, and in here I just write two vectors, 0, 4, and then 12. Another one is 0, 2, and 1, right? And I expand this along the first column because we have more zeros in this column. So I can write that is just I. Another one is 4, 12, and 2, 1. And you can find this number that is just, you know, 4 minus 24 I, which is negative 20I. So you already have direction vector of the tangent line. This is nothing but negative 20, 0, and then 0. And from here you can write the equation of that straight line, okay, which is passing through the point 0, 1, and 3. So you will have x equal to negative 20 t, because the x0 coordinate is 0, and the y is equal to 1 plus 0 t, so that's why you have just 1, and the z is equal to 3. So that is the solution of this problem. Another problem for today is to find the angle of inclination of a plane. So you can see the picture on the screen. So if you have a plane and you need to find the angle of inclination, basically you need to find the angle theta, right? So you know n is the normal vector to this plane, and k, actually that is the z-axis, right? The direction of the z is the normal vector to the x or y plane. So in order to find the angle theta, that means the angle of inclination of the plane, we just need to find the angle between n and k. Make sense? So we already have the formula from very first chapter of this course. The cosine equal to the norm, the absolute of dot product divided by the norm of n and k, right here, of the n and k. But the norm of k is 1, you know, because k plays like 0, 0, 1. So the norm of k is 1. So that's why cosine of theta of the angle of inclination of a plane is just, you know, dot product. And with the k, you take the absolute and you divide by the norm of n. That's it. And you know, if you have a plane, right, you know how to find a normal vector. Okay. So now let's solve one example and then we finish today's lecture. Let's consider the following example. They ask us to find the angle of the inclination of the tangent plane to the ellipsoid. Ellipsis looks like x squared over 12 plus y squared over 12 plus z squared over 3 equal to 1, and the point is 2, 2, 1. So now they ask us to find the tangent plane first. So I have typo in here. The tangent plane, and then we need to find the angle of the inclination of that tangent plane. So first, let's do the tangent plane, right? So the first step is tangent plane. We need to find tangent plane. The tangent plane, of course, we need to find normal vector, right? Normal vector. But actually, we don't have to find a tangent plane because they just ask us to find, you know, the angle of inclination. So for us, normal vector is enough. You see, just normal vector is enough. Why? Because we know the angle. Oh, what happened with this? Because we know the angle cosine of theta is just, you know, absolute of the normal vector dot product with the k, right? I can write k is just 0, 0, 1. Don't forget that. Divide by the norm of n. So we don't have to find the tangent plane, okay? We just need to find the normal vector, right? So we know from previous examples that the normal vector is just, you know, gradient of f capital, where f capital is the function of x, y, and z, okay? So we just need to find gradient of f, where f is equal to x squared over 12 plus y squared over 12 plus z squared over 3 minus 1. So I will find gradient of this function, x and y and z, that is just equal to x over 6, y over 6, and then 2z over 3, right? And then I plug the point 2 to 1 into this. Here's 2 to 1. 2 to 1 into this. So I have, gradient of f at 2 to 1. It's just, 2 over 6. 2 over 6 and then 2 over 3. Which is, let's simplify this, 1/3, 1/3, and then 2/3. All right, so we already have normal vector. Now I can find, the angle. So the formula looks like dot product of gradient f 2 to 1 with, I write here 0, 0, 1, okay? Take absolute and then divide by the norm of gradient of f at 2 to 1. Okay, so that is 1/3, 1/3, 2/3, dot product with 0, 0, 1. Just absolute, divide by the norm of this guy, so vector, so you have square root, right? 1/3 square plus 1/3 square plus 2/3 square, right? So overall, on the top you have 1/3 with 0 is 0, and then 1/3 with 0 is 0, so you have 2/3 times 1, which is 2/3, right? In the bottom, you have square root of, I would say, we have 1/3 square, another 1/3 square, and another 4/3 square. This is 4 times 1/3 square, right? So basically we have 1, 1, and 4, but that means we have 6 1/3 square in here. Make sense? So I will write that is 2/3. Let's write that like 2/3, right? And then 1/3, and then square root of 6. And now we simplify 1/3 and 2/3. We get just 2 over square root of 6. So since we have cosine of this, you can you apply a cosine. From here you get theta is equal to a cosine of 2 over square root of 6, which is approximately equal to 35.3 degrees. So we finished this problem. Okay, so by doing so, we finished this section. This section, I think, is pretty easy and very clear enough, because basically we only need to work with gradient. And let me repeat that again in here, right? The most important idea is, you want tangent plane, you need a normal vector. And what is normal vector? That is the gradient of the function, f capital. Okay, and this is very interesting because that relates to the level surface, and we use very good, very important property of gradient is, gradient vector is perpendicular to level surfaces. All right, so thank you for watching, and if you have any questions, please email me. Okay, I will respond within 3 hours, but make sure that you send me email before 7 p.m. every day. Thank you.